Namaste dosto. Imagine you scored marks in a test and your friend scored too. Now, if everyone's marks are almost the same, that means the scores have low spread. But if some got very high and others very low, that's a high spread. Today, we are going to explore a special number that measures exactly how spread out data is. It's called variance. Variance tells us how much the data values deviate from the average, but squared. Why squared? Well, this way, we don't have negative differences cancelling out positives, so all deviations count positively. Mathematically, we write variance as sigma squared. That's the Greek letter sigma raised to power 2. For a whole population, variance equals 1 divided by n, the total number of data points multiplied by the sum of each value minus the mean, all squared. In words, that sigma squared equals 1 over n times the sum from I equals 1 to n of open bracket x sub I minus x bar close bracket squared. Here, x sub I is each data value, and x bar is the average. If variance is high, it means values are spread far from the mean. Low variance means values cluster close to the mean. Remember, since we square deviations, variance can never be negative. It's always 0 or more. Picture a simple line graph with data points scattered, a line showing the mean, and arrows representing these squared distances. You can visually see variance as the sum of those squared arrows. So next time you wonder how different scores or measurements vary together, variance is your go-to measure. Continuing from variance in simple data, what if our data is grouped? Like marks grouped in intervals, say 0 to 10, 10 to 20, and so on, and frequencies tell how many fall into each interval. Here, calculating variance directly value by value would be tedious. Instead, we use class marks, which are midpoints of each class. For example, for the class 0 to 10, the class mark is the midpoint 0 plus 10 divided by 2, giving 5. We denote class marks as x sub I. Then, to include frequencies, we calculate variance by summing over all classes the frequency times the square of the deviation of class mark from the mean, divided by the total frequency. The formula is sigma squared equals sum over I of f sub I times open bracket x sub I minus x bar close bracket squared, all divided by sum over I of f sub I. This way, group data variance accurately reflects the spread of data that's stored in intervals. For large data, there's also a clever step deviation method, but at its heart, the key idea is using class marks and frequencies weighted properly. Imagine a frequency table with columns for class intervals, class marks, frequencies, and squares of deviations multiplied by frequencies. It all adds up to find variance for group data. Now that we have variance, which measure spread squared, comes an important question. What about the original units? Variance is in squared units, which is hard to interpret directly. If marks are in points, variance is in points squared, not very relatable. That's where standard deviation, or SD, steps in. Standard deviation is simply the square root of variance, bringing us back to the original data units. We write it as sigma equals square root of 1 over n times sum of x sub I minus x bar squared, or sigma equals square root of sigma squared when considering group data. This means, if variance was big because squared units inflated it, standard deviation shrinks it back to a useful scale. Standard deviation helps compare variability directly and is widely used in fields like finance, reliability testing, and physics to understand how data fluctuates from the average. Picture a histogram showing data distribution with a marked mean line and a shaded region covering one standard deviation on either side. This visually shows where most data lie, within one standard deviation of the mean. So, standard deviation gives a much easier way to talk about spread in real-world units. Sometimes, computing variance from scratch is slow because you must find every deviation, square it, then sum it up. But there's a quicker, practical formula called the shortcut method, great for exams or fast calculations. For data without groups, variance equals sum of squares of all observations divided by n minus the square of the mean. Mathematically, Sigma squared equals sum of x sub I squared over n minus x bar squared. Here, sum of x sub I squared means you add up each data point squared, then divide by total number n and subtract the square of the average. For frequency data, variance equals sum over I of frequency times square of class mark divided by total frequency minus square of the mean. That is, sigma squared equals sum of f sub I times x sub I squared over total frequency minus x bar squared. This shortcut avoids calculating each difference from the mean and squaring separately, saving valuable time during exams. Imagine a table with columns of data values, squares of data values, frequencies, and products of frequency times squared data. This helps organize computations efficiently. Let's see this in action with a solved example. Suppose we have marks scored by students grouped into class intervals, each with a frequency. Step 1. Find class marks. For each interval, add lower and upper limits and divide by 2. Step 2. Compute the mean x bar by summing frequency times class mark for all classes and dividing by total frequency. Step 3. Find the sum of frequency times class mark squared. Now, use the shortcut variance formula. Variance sigma squared equals sum of f sub I times x sub I squared divided by sum of frequencies minus square of the mean. Finally, standard deviation sigma is the square root of variance. Picture a complete table listing class intervals, frequencies, class marks, squares of class marks, and their frequency products, all worked out step by step. This method ensures you get the standard deviation for group data efficiently and accurately. After calculating standard deviation, how do we compare variability between two very different datasets? For example, one might be test scores out of 100, another monthly sales in thousands. Enter the coefficient of variation, or CV, a unit-free relative measure of dispersion. CV equals standard deviation divided by mean, multiplied by 100%. This means CV tells us the spread relative to the average. A lower CV means less relative variability. That is, more consistency or efficiency. CV finds big use in economics and industries where you want to compare performance or risk across data with different units or scales. Imagine a bar graph showing two datasets side by side, each labeled with their mean and standard deviation, then their CVs compared. This gives a quick visual grasp of relative variability. Let's quickly recap what we've learned today. First, variance equals 1 over total number times sum of squared deviations from the mean. Sigma squared equals 1 over n times sum of open bracket x sub I minus x bar close bracket squared. Second, standard deviation sigma is square root of variance. Sigma equals square root of sigma squared. Third, coefficient of variation CV equals standard deviation divided by mean times 100%. Remember, variance measures squared deviations, giving a numerical spread, while standard deviation brings it back to original units for easier interpretation. Shortcut formulas help you calculate variance swiftly, especially useful in exams. When dealing with group data, remember to use class marks and frequencies for accurate estimation. Finally, CV helps compare spread across different datasets on a fair, unit-free scale. Allez va! You're now equipped with solid tools to measure and understand data variability, essential knowledge for your exams and real life. Before we finish, here's a quick question. If two datasets have the same standard deviation but different means, which one has higher coefficient of variation? Think and answer. Great job today. Keep practicing, and this topic will become as easy as your favorite cricket scorecard. Shabash!